Swayam Prabha. Digital India. Educated India.
So, good morning, good afternoon. Welcome back to our course on analysis and design of rigid pavements. We are currently in module 3 of our course. So, our entire course is divided into 4 modules and we are almost done with the third module. So, module 1 was an overall introduction. We learned about the different types of rigid pavements. In particular, we learned there are 4 types of rigid pavements. There is JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and PCP or pre-stressed concrete pavements. Now, among these we learned that JRCP is very rarely used and PCP is used more in specialized applications, for example in airports. And so therefore our course is mainly devoted to JPCP and CRCP. Now, even then you might have noticed so far we've only been talking about JPCP. So CRCP analysis tracks very closely along with JPCP analysis. So although I've only been focusing on JPCP so far, in truth JPCP and CRCP track together, so we have been studying both. The two diverge when it comes to the point of design, but design is something we learn in module 4. So that was module 1. Now modules 2 and modules 3 we've been learning about the analysis of rigid pavements. Why are we studying about analysis in such great detail? Almost half the class is devoted to analysis. Simply because modern design philosophy, and we learn more of this in module 3 or in module 4, modern design philosophy is essentially iterative in nature. That is, design is an iterative analysis procedure. We choose some sort of a test case, we choose some sort of a trial case, and we perform an analysis and we see whether the solution is within some expected limits. If it's not, then we go back, we update our trial case, and then again we do analysis. So in order to do design, we really need to be very proficient at doing analysis, and that's why we've been spending some time in doing analysis. Now, in module 2, we studied the analysis of rigid pavements using classical methods. So classical methods is fundamentally the old methods. They are the older methods which have been developed almost 100 years ago at this point. Starting of course with the method of Westergaard, that was Professor Harold M. Westergaard at the University of Illinois. So he developed the first method for analysis of JPCP pavements, but he developed it only for a single pavement or a single slab. He showed that if you place the load at the middle of the slab such that all the 4 joints are very far away from the load, or if you place it at the corner of the slab such that 2 of the joints are near the load, or if you place it at the middle of one of the edges such that 3 of the joints are very far away from the load, then he gave us certain formulas which allow us to calculate the stresses and the critical stresses and displacements in the slab for these 3 loading conditions. Now, of course, one of the shortcomings of this method, there are several shortcomings of Westergaard's method. One of them was the so-called large slab assumption. The other assumption was that the load is always circular. Of course, the circular load part has been overcome over time. So we've gone from being only able to do circular loads to being able to do square or rectangular loads using analytical methods. That's not much to say because actually in practice, actual loads, as we saw earlier, are neither circular nor square or rectangular. They actually have a fairly complex footprint of the tire, and taking that complex footprint into account using analytical methods is pretty hard. Now, one more thing we learned among the analytical methods, besides Westergaard's theory and subsequent modifications, is the theory of double bars in joints. So what we learned is that rigid pavements, or JPCP in particular, JPCP tends to have joints because joints are essentially what leads to reduction of stresses. It is possible to make a pavement that has a rigid pavement that has no joints, but the stresses would be so high that they would crack almost instantly. And so if you want to prevent cracking, there are ways to do it without joints also, and that's what CRCP is. But if you want to prevent cracking, then we need to have regularly spaced joints. We need to make the slabs from an infinite size to a finite size. In that process, then, we have to do something about the joint. We could leave the joints plain, but generally it's been seen if you leave the joints plain, then there is a lot of stress which develops in the slab itself. And it doesn't really make sense for one slab to be taking so much stress when there are so many other slabs around it which can bear some of that stress. And that's why dowel bars are used in joints to transfer load from one slab to another slab so that the entire slab system participates in the load transfer mechanism instead of only a single slab doing it. Now, for analysis of dowel bars, it can get fairly complicated, but we learned a somewhat straightforward theory, which is called Freiberg theory, that we learned back in module 2. Freiberg essentially showed us that if you have dowel bars, then the dowel bars during load transfer, they exert a compressive stress, and that's probably one of the first times in civil engineering you're seeing compressive stress as a failure mechanism. It exerts a compressive stress on the surrounding concrete, and as a result of that, and basically that compressive stress is the means by which load transfer happens from one slab to another slab. And we also learned that according to Freiberg theory, the compressive stress has to be limited to some sort of bearing strength, and that bearing strength is mainly obtained through experimental findings. There's not a very good mechanistic way to calculate it. Now, one interesting aspect of Freiberg theory is that Freiberg theory can analyze a single dowel or can analyze a system of dowels, and we learned how to do analysis of system of dowels using Freiberg's theory. However, the shortcoming is that the dowels and the slab are essentially completely uncoupled from each other. That is, Freiberg theory tells us how to calculate the bearing stresses on the slab due to the dowels, but it tells us nothing of how the presence of the dowels or the presence of the bearing stress has an effect on the response of the slab itself. This is what I mean by the two being completely uncoupled. In Freiberg theory, we still use Westergaard's theory to analyze the slabs, and separately we use Freiberg theory to analyze the joints or the dowels. But in truth, if you look at it physically, set the mathematics aside, if you look at it physically, the two are acting and behaving together as one. And analyzing that using an analytical method has proven to be quite hard. It's for these reasons, the shortcomings of Westergaard's theory, the shortcomings of Freiberg theory, that we have now come to using, in the modern day analysis of rigid pavements, we now use the finite element method. So, in this module 3, we have been looking at the analysis of rigid pavements using numerical methods, in particular the finite element method. Now, I have been emphasizing, and I will emphasize again, that the finite element method is a vast topic. It's definitely not something you can learn in 2 or 3 lectures in a course on pavement design. And for those of you who are civil or mechanical engineers, you should definitely be taking a standalone course on finite element method to fully understand and appreciate what it's about and how it works. But I'm trying here in this course to just give you a very, very brief outline and only explain those aspects that you need. Now, one of the things we learned about the finite element method, and indeed any numerical method, is we kind of make a very astonishing assumption, and the astonishing assumption is that we give up on the idea of getting an accurate solution. Remember, when analytical solutions were derived, now analytical solutions are based on a series of assumptions. Westergaard's theory assumption, circular loading, infinite slab, tensionless springs, etc. There are a number of assumptions that Westergaard's theory makes. Whether the assumptions are reasonable or not is a different matter. But as long as the assumptions are accepted, then the solution is exact. There is no error whatsoever in the solution. That's why we call it an analytical solution. On the other hand, numerical methods do not make many of those assumptions. They make other assumptions, but they don't make the same assumptions as Westergaard's theory or analytical methods. And they start with one of the key assumptions, that there is always an error. And then they hope, as we saw, that the error may be regarded as a residual function, R of x, and it is hoped that if we multiply that by some weight function, whatever that weight function might be, and we sum it up over the entire domain, so integral WR dx, if we sum it up over the entire domain, then we hope that this is 0. That is, we are not saying that our error is 0 everywhere. We give up on that idea altogether. Instead, we hope that the total weighted error throughout the entire domain is 0, and that is the basic motivation of the finite element method. And one of the ideas and key ideas in the finite element method is that if we have a small number of elements, that if we take our domain, our JPCP slab in this case, if we take our domain and we divide it into smaller elements, well, we start by dividing into smaller elements, and as the number of elements increases, that is, as the number of elements tends to infinity, we hope that the error tends to 0. So, we do not say the error is 0. We say that if we could have an infinite number of elements, which is theoretical, you can't have an infinite number of elements, but we hope that if we have a large number of elements, the error is small enough that from a practical perspective, we don't care. Why do I say from a practical perspective? Well, because after all, we can do whatever designs we want in an office. We can design it on paper, we can design it on a computer. But when you go out in the field, other limitations occur. there are construction deficiencies, there are variability in materials, there are variability in manpower as well as variability in workmanship. All of these are going to lead to some variances on the field anyway. So there are definitely going to be some error between our analytical solution as well as our field solution, whatever we're getting on the field. And so the idea of the finite element method is, why not just have some error in the solution also and hope that both the field error and the numerical error, they somewhat cancel each other out in the end. So that's why we've been studying in module 3 the finite element method. Now let's do a quick recollection before we go into today's lecture proper. So today's lecture we're going to see how joints can be analyzed using the finite element method. So dowels in particular in joints, how they can be analyzed using the finite element method. And as you'll see, it's very different from Freiberg's theory. In this case, we are actually able to couple the dowel as well as the joint as well as the slabs. But it can also start getting increasingly complicated, and you do have to know quite a lot of theory to understand it. So this lecture coupled with the next lecture is probably going to be the most mathematically intense of all the lectures that we cover in this course, but I'll try to guide you through only the important parts of it without bogging you down too much in the mathematics. So in today's lecture, the objectives are, we are going to use springs and beams to model joints in JPCP using finite element methods. Again, I assume all of you have at least a civil engineering background or maybe a mechanical engineering background, so you at least know what a beam is, and if not, we'll give a quick review of that in a few minutes. Okay, so let's recall how did we use the finite element method for analyzing JPCP, a single JPCP slab, before getting into joints. Now recall that basically in the finite element method, we are solving a differential equation, possibly with some boundary conditions. We are solving a differential equation approximately. So we have to ask ourselves, for a slab, what is the differential equation which is going to govern our analysis? And that answer actually Westergaard gave a long time ago, but fundamentally it was given by Sophie-Germain. So this equation we've seen in the past. This was the Sophie-Germain equation. Let me write it down. Sophie-Germain equation. So this is the Sophie-Germain equation that we saw in the past. This is basically used for the deflection in a medium thick plate. So in a medium thick plate, we basically have an assumption that we have a neutral plane, and all rotation, all the deflections, any surface, any plane which is perpendicular to the neutral plane before deflection remains perpendicular after deflection, and therefore no transverse shear is admitted. Please go back to the lecture. In module 2, I had an introductory lecture where we derived this equation and we explained the assumptions. So you want to go back there to just get a refresher in case you forgot this. But looking at the terms here, so W is that deflection. Again, the deflection, if we look at it from a cross-sectional perspective, the deflection W is constant across the depth Z, and therefore W is not a function of Z. But W can change at different points on the surface. So W is a function of X and Y. So this is the vertical or transverse displacement of the slab. So what we have is d into del power 4W. So this is a biharmonic operator, del power 4, plus Kw is equal to minus Q. Here K is the coefficient of subgrade reaction. It's basically a correction we add to the Sophie-Germain equation to account for the fact that our JPCP slabs, their boundary conditions are that they are sitting on a bed of springs. That's what we called a Winkler foundation. Let me write that down. So this was a Winkler foundation assumption that we made, and that's where this K value comes from. So that is the correction essentially of the Sophie-Germain equation. But what we have here, we have some d into del power W, that's the stiffness, and that is equal to some Q, which is the external transverse load which is being applied. Now this d we defined previously, this is basically the plate stiffness. If those of you who are civil or mechanical engineers and you studied beams, you would have remembered the flexural stiffness of a beam. This is the analogy of it. This is the plate stiffness of a thin plate and of a medium thick plate. So that is EH cube divided by 12 into 1 minus nu square, where E is the Young's modulus, nu is the Poisson ratio, we've seen these before, and the thickness, the entire effect of the thickness. Since we said that there is no displacement along the Z direction, the entire effect of the thickness of the slab is contained inside this D term, and it is H cube. So the stiffness of the plate actually increases as the cube of the thickness of the plate. So you can imagine it becomes stiff very, very quickly. So even small changes in thickness have a large effect. So this was the fundamental equation that we derived. Westergaard had gone on to provide analytical solutions for this. But what we saw in the previous lecture is, if we step aside from analytical solutions, we can solve this using the finite element method. There are many sort of methods or techniques you can use to solve it using FEM, but we learned a particular method using what's called an MCZ element. And in the previous lectures, I had explained what it is. Briefly, we assume that if we have a plate, now one assumption of the finite element method is we are not going to solve our solution at every point. Instead, we are going to solve our solution at a discrete set of points which we call nodes. So, these are nodes. We solve it as a discrete set of points which are called nodes, and in between the nodes, we are going to assume some sort of simple polynomial interpolation in between them. So, what we saw for an MCZ element, each node basically has 3 values which have to be calculated. Those values are called the degree of freedom. So, obviously, one degree of freedom is W, the displacement itself. But the other degrees of freedom, if I draw the coordinate system here X and another coordinate system Y, so we have W, which is basically in the Z direction, that's through the screen. And then we have rotation about the X axis that we call del theta X, that's del W over del X. And we have rotation about the Y axis, that's del W over del Y. So, we've got this del W over del X as well as del W over del Y, and these 3 constitute our degrees of freedom per node. So, when we are trying to solve for a single plate and a single element, when we are trying to solve using the finite element method, we are essentially reducing the problem to evaluating 3 degrees of freedom per node, where every node basically belongs to an element, and the MCZ element is basically a rectangular plate element. There are other plate elements also. We can have a triangular plate element, it's called an Argus plate element. There are a variety of elements. Anyway, it's not important for us to know all the elements, we just studied the MCZ element. So, this is what we have for the MCZ element. So, naturally because it's rectangular, one element has 4 nodes, and we have 3 degrees of freedom DOFs per node, and so totally one element is 4 into 3 is equal to 12 DOFs. So, we saw this, and what we saw then is if we go on and use the finite element method, we do all the mathematics, weighted residual, etc. I am not going to repeat that, and truly speaking, you should be taking a full course in the finite element method to fully understand it. But if we go and do all of these calculations, what we eventually saw that we could reduce our entire system. Again, our system was basically this differential equation. We could reduce it into a series of algebraic equations, and it's not actually going to be a small number of algebraic equations. So, let's illustrate. So, for example, if we had just one element, if we approximated our entire slab with just one element, which is not a very good approximation. Remember, our error will go to 0 only as the number of elements becomes very large, and so having just one element is obviously not very large. But if we have just one element, then our differential equation, which is the Sophie-Germain equation, it actually reduces to 12 simultaneous linear equations, and that can be shown as very compact form. KE is equal to FE, where K is what we called the local stiffness matrix. It is the stiffness matrix of our 12 degree of freedom element, our 4-noded MCZ element. This was called the local stiffness matrix. Let me write down matrix. And UE, of course, was the vector of the degrees of freedom. So, that UE we could have written as a vector as W1, theta x1, theta y1, so on till W4, theta x4, theta y4, and so on. And FE, of course, is any external load, the equivalent external node that we are applying. So, we saw in the last class how to analyze this. Now, that gives us then a 12 by 12. So, KE is 12 by 12. KE is always going to be 12 by 12 because KE is the local stiffness matrix, and locally the element consists of 12 degrees of freedom, and we learned last time that our stiffness matrix is basically going to be of size total number of degrees of freedom by total number of degrees of freedom. So, because our number of degrees of freedom for one element is 12, the local stiffness matrix KE is going to be of size 12 by 12. Well, that's pretty easy. We can wash our hands away that now we have a 12 by 12 system. I can give it to you as an assignment to solve, and you'll probably take the next few months to solve it. Well, again, that's not what we do in practice. As we shall see about 2 lectures from now, in the finite element method, although it's very important to understand the formulation, it's important to understand where these values come from. But in practice in FEM, we always solve using a computer program. So, we saw with Westergaard's theory as well as Freiberg theory, we could solve it by hand, we could solve it by a calculator. At most, we could type it up on some sort of a spreadsheet program and get a solution. That's not the case for finite element methods. They are much more complicated than that, and so we have to do more effort. Fortunately, people before have already done the effort, and they've already created software programs that can do these calculations for us. We'll see more about that about 2 lectures from now. Now, coming back to what I had said about error. So, KE UE is equal to FE, this equation over here. This is well and good if we have one element. However, as we know that we need to have a lot of elements in order to get a reasonably accurate solution. In that case, we have to divide the slab into more than one element. That is, we have to have more nodes. And so, for example, if this was my slab, previously I had shown that I had just 4 nodes and therefore one element. This is not enough. We may have to divide it further. So, for example, along each direction, I'll divide into more nodes, and then now I, instead of a 1 element approximation to the slab, I have a 4 element approximation slab. Similarly, I can have a 9 element, 16 element approximation, and so on. So we can have we usually need to have many more elements in order to approximate the behavior of the slab. In that case, in the previous lecture in the introduction to finite elements, we learned a technique called assembling a global stiffness matrix. In assembling a global stiffness matrix, we make use of an important assumption which I called local support. So local support basically says that any elements which are directly connected to each other have a corresponding entry in the stiffness matrix, and any nodes which are not connected to each other have a corresponding entry in the stiffness matrix which is 0. You want to go back to that lecture and see the process of what we call assembling the global stiffness matrix. It was not particularly difficult, but it was a little bit involved of a process. And we'll come back to a little bit of it today as we move forward in today's lecture. But we learned this process of assembling a stiffness matrix, and what we saw is that we can eventually, for each of these individual elements, we have Ke. And then we can take that together and assemble Kg, which we called as the global stiffness matrix. Let me write that down. So we call this Kg as the global stiffness matrix. So we have the global stiffness matrix, we have the vector of the global degrees of freedom, and we have a vector of global forces, global transverse forces acting on the slab. We have all of these together, and taken together then, now we can solve for the entire system. So the entire physics of the system, with the assumption of local support, is contained in this simple one-line compact form Kg Ug is equal to Fg. But it's simple, but it's equally complicated, because if we consider this diagram which I drew over here, here we have 5 nodes in this direction, we have 5 nodes in this direction, so totally we have 25 nodes. Each node has 3 degrees of freedom, and therefore this is a 75 degree of freedom system. So our K is actually 75 by 75, and therefore we have to solve 75 simultaneous equations at one time. And even this is a relatively small approximation. Usually you have to do even more than that. We'll see that in later lectures. But again, as I emphasize, in reality, a computer is going to be solving this for us. So we are going to use a computer program to do these solutions. For us as human beings, solving 75 by 75 is basically too much. We can't do it. For a computer, 75 by 75 is actually a relatively small system. It's not very difficult for a computer to solve it. And so we'll see these things as we go forward later in these coming series of lectures. All right. So all our discussion so far was basically for one slab. So we discussed that we can do a 1 element approximation to a slab, we can do a 4 element approximation, 16 element approximation, etc. All that was one slab. But obviously, a JPCP section is not one slab. JPCP consists of many slabs. And so now because you have so many different slabs, how do we analyze the fact that we have multiple slabs? If you recall, and this is actually a pretty big jump that we're making, if you recall Westergaard's theory as well as subsequent modifications, we studied that in module 2, we only discussed one slab. Even when we had joints, we discussed the failure of the dowels at the joints, but we never discussed how the presence of multiple slabs and some connection between them, how is it affecting the behavior of the slab itself. We studied each slab on its own as though it had no relationship with any adjacent slabs. So if I try to illustrate this point using a figure, what I have over here, so I've got here a 2 by 2 system, so I've got a 4 element system here. So I've got a 4 element system over here, and I've got another 4 element system over here. So these are 2 slabs. Each has been approximated by a 4 element system. I can calculate the stiffness matrix Kg for the slab on the left. I can calculate Kg for the slab on the right. We just discussed how to do that. What do we do about the fact that there's a connection between the two? That is, the fact that the slabs are connected due to some load transfer effect. That could be due to base friction, that could be due to aggregate interlock, that could be due to dowels. Whatever is the mechanism of load support, how do I model that into using the finite element method? That is a question that we have to deeply consider. Analytically doing it is actually quite difficult. As we saw that as I said before, Freiberg theory is essentially uncoupling these two. The dowels are analyzed separately, the slabs are analyzed separately. We are not doing an integrated analysis of slabs and dowels. And that's a significant shortcoming in the analytical methods. Finite element method, as it turns out, this is not a problem at all. In fact, it's relatively simple to solve this problem. Of course, you have to understand the physics, but if you understand the physics of the problem, it's not a very difficult problem to solve. That's also one of the remarkable things about the finite element method, this ability to analyze multiple physics through an integrated approach. Let's see what I mean. Let me try to redefine the stiffness matrix. So far we've been talking about the stiffness matrix as sort of a mathematical formulation. But the stiffness matrix also means something physically. The stiffness matrix in FEM is basically an interaction between the degrees of freedom, and that interaction is defined by the physics that's specified by the differential equation. So for example, if I again consider one element, so in one element, this entire element is defined by the Sophie-Germain equation. So this has been defined by the Sophie-Germain equation, that's our physics. And we saw that approximating this physics, we can come up with a stiffness matrix. Now, that stiffness matrix is basically telling us, for example, if there is a change in W1, if this is 1, 2, 3, 4, if this is node 1 and degree of freedom is W1, if there is a change in W1, then what is the corresponding change in, let's say, theta Y3 or theta X4? The stiffness matrix is basically telling us how one degree of freedom interacts with another degree of freedom. That's sort of the physical meaning of what a mathematical function, which the stiffness matrix really is. So, and that interaction, of course, is defined by the governing equation, which is the Sophie-Germain equation in this case. So, if we look at the stiffness matrix in these terms, so what we have in this figure over here, so we basically have 4 elements here, 1, 2, 3, 4. We have 4 elements here. Each of them has a stiffness matrix, and we assemble the global stiffness matrix assuming local support. So now we have a matrix which is telling us how this node, how the degrees of freedom of this node are interacting with the degrees of freedom of this node. Similarly, for the next slab, we have the stiffness matrix here telling us how the degrees of freedom of this node are interacting with the degrees of freedom of this node and other nodes. So therefore, what we really need in order to understand how the joint is affecting the behavior of the two slabs, our problem actually reduces to understanding what is the interaction between the nodes which are across a joint. In other words, this node which I am highlighting here, what is the interaction of this node on the left slab with this node which I am highlighting on the right slab? What sort of interaction do we have between them? If we can incorporate that interaction into the global stiffness matrix of the entire system. Just as a note, so what is the global stiffness matrix of the entire system? If you look at this left slab, we have 27 degrees of freedom. That's basically we have 3 nodes. Well, if 3 into 3, so we have 9 nodes and each has 3 degrees of freedom. So 9 3 is 27 degrees of freedom. The right slab also has 27 degrees of freedom. Therefore, the total number of degrees of freedom of this 2 slab system is 54. So really, all we have to do in our stiffness matrix is we have to figure out how to connect these degrees of freedom which are across a joint. If we can figure out how to incorporate that into the stiffness matrix, then we have effectively created a connection between the 2 slabs using the finite element method. It's really remarkable if you think about it. This is very difficult to do using analytical methods, to be able to integrate in an integrated manner, to have one set of equations which gives us the behavior of both the slab and the dowel or the joint is pretty hard. In the finite element method, it reduces to just adding some more terms in the stiffness matrix that account for interaction between certain degrees of freedom. So, as I wrote over here, so each element of Ke and Kg defines the interaction between the degrees of freedom. And so, really, joints can be modeled as interactions between degrees of freedom. That's a very simplified way to look at joints, and it gives us the opening to do this integrated analysis of slabs and joints. But it comes down to a question. So, as I wrote over here, the interaction, so the stiffness matrix is basically the interaction between the degrees of freedom, that's fine. But that interaction has to be defined by certain physics. For individual slab, the physics is straightforward, the physics is the Sophie-Germain equation. What about the joints? What physics are joints going to follow? If we can answer this question, then we have essentially solved our problem of integrated analysis of joints and slabs. But as we shall see, this is not such a straightforward question to answer. And in today's lecture, as well as in the next lecture, we will actually take some effort to see how different researchers have tried to address this very problem. It is not a very straightforward problem to answer what is the physics of the joint. Okay. So, let's try to, before we go into the actual solution, of course, many people have done it and I'm going to tell you what are different approaches for modeling the physics of the joint. But before we do that, let's try to just pause and understand what would the physics look like. Before we go into what the actual physics is, what would the physics look like? Okay, so we have been talking about the fact that the purpose of interaction between joints is load transfer. That when you have a load on one slab, then we would like some of that load to be carried over to the other slab. So the two slabs are participating in carrying the load instead of one slab doing on its own. So this load transfer over here is basically what the interaction of the joints between the slabs is. Put in a different way, the purpose of analyzing joints is basically to understand how load is being transferred from one slab to another slab. So the interaction that we are thinking about is as follows. We previously described that we have two slabs. We have an approach slab A, which is on the left over here, and we have a leaf slab L, which is on the right. And we have a load which is on the approach slab. Now, we had seen earlier that if our load is such that if our joint is such that there is absolutely no load transfer, that's a very poor condition to have, but let's say that is the case. If we have a case where there is absolutely no load transfer between the joints, then basically when we have a load on the approach slab, we are going to have a deflection at the approach slab, at the edge of the approach slab, and then we will not have any corresponding deflection on the corresponding side of the leaf slab. So over here, this value would be equal to 0 if there is absolutely no load transfer. Now, naturally, if there is some load transfer, which is what we would expect to have in joints, if there is some load transfer, then if WA is not equal to 0, which it's not because there is a load, then WL will also not be equal to 0. That's basically what load transfer is. So one way to understand how to model joints is that it's somehow an interaction between W. If you have the joint, of course drawing in an exaggerated way, but if you have nodes across from each other at joints, then W is basically some sort of connection. The joint is basically some sort of connection between the W degrees of freedom of nodes which are facing across each other from the joints. So, and that's a fundamental idea. So again, the interaction is basically between the W's, between the displacement degrees of freedom. It happens to be between the rotational degrees of freedom. We'll talk about that in a second. But now, just as an overview, we can understand that the interaction is basically an interaction between the displacement degrees of freedom. So how do we model the interaction between two degrees of freedom? So as it turns out, there are many ways to do it, but as it turns out, in the finite element world, so in the world of computational mechanics, we have an absolutely favorite type of element, and that is a spring element. So as computational mechanists, we absolutely love analyzing anything as springs because it's just very, very easy to do it. So what's a spring? You've all studied springs in the past. So springs you've learned is F is equal to K delta X. So basically it's an element whose force is, whose displacement is linearly proportional to the force. And so if I apply a displacement of delta X, then the force or stress developed is going to be proportional, and there's a proportionality constant which we call the Spring's constant or the spring stiffness, K. So we've already learned this. Now, you might have learned this equation back in 11th class or 12th class, somewhere in high school. What you may not have learned is the finite element approximation to this. So in the finite element world, if we have a spring of two nodes, nodes 1 and node 2, each of them basically only has 1 degree of freedom. So we have U1 and U2. Then we can basically write this as some Ku is equal to F, where F1 and F2 are the loads at each node. And so we have K into U1, U2 is equal to F1, F2. And this K, we can actually just derive it using this equation over here. It's not particularly difficult, but it's not necessary to go into details. This K is basically the form I've shown here. So where K is, the lowercase k is the spring stiffness matrix, then the spring stiffness. Then the stiffness matrix of the spring element is this K, K. You will note again, this is symmetric, as it should be. And you will also note that this has 2 degrees of freedom. Naturally, we saw there's node 1, node 2, each of them has 1 degree of freedom, and therefore the total degrees of freedom of a spring element is 2. So we have a 2 degree of freedom system, and therefore our stiffness matrix is 2 by 2, as we would expect. Now, why do we talk about this? Well, as I said, our joint can be modeled as an interaction between W on the approach slab and W on the leaf slab for nodes which are facing each other. And so the easiest way to model this approximation, if instead of U1, U2 here, I wrote it as W1, W2, then basically I have a vertical spring that is connecting these vertical or transverse degrees of freedom or transverse displacements. And so we can model a joint as a spring interaction between adjacent Wi degrees of freedom, that is W on one side of the slab and W on another side of the slab. This is a pretty amazing idea if you think of it. We have found, whereas it's difficult to do an integrated analysis between two slabs analytically, if basically we can specify the spring constant, then we have fully analyzed what is the interaction between the slab across joints, something that was difficult to do analytically. So if we look at it back from our original problem, so we were looking at a problem where we had 4 elements on this side and we had 4 elements on that side, and then we had a joint across it. So now what I've done here is I've numbered the nodes. So I've got on the first side, I've got nodes 1, 2, 3, and 1, 2, 3, and then lower side I'm continuing 4, 5, 6. So on the left side system, I've got 9 nodes, 1, 2, 3, 7, 8, 9, 13, 14, 15. On the right side, I've got 4, 5, 6, 10, 11, 12, 16, 17, and 18. So what I see here is that nodes 3 and nodes 4 are across from each other, and I've chosen this numbering scheme exactly to take advantage of this. Node 9 and node 10 are across from each other, and node 15 and node 16 are across from each other. Therefore, the interaction, if we model the joint as an interaction between the W degrees of freedom, then the interaction is basically going to be between W3 and W4, and then here W9 and W10, and here W15 and W16. Again, there can be an interaction which is based on the rotational degrees of freedom also. Right now, I'm looking at it as only an interaction between the displacement degrees of freedom. So what is this interaction? Well, the interaction is defined by this stiffness matrix, which we saw previously. This is the spring stiffness matrix. And so if I have the global stiffness matrix, which connects these 4 elements with each other, as well as with the 4 elements here, to that global stiffness matrix at degree of freedom 3 and degree of freedom 4, that is on row 3 column 4 and row 4 column 3. All I have to do is I have to add in this as well as row 3 column 3 and row 4 column 4. All I do is I add or assemble this stiffness matrix into that global stiffness matrix at degrees of freedom corresponding to W3, W4, W9, W10 and W15, W16. If I assemble this together, then I have successfully incorporated this spring physics, the physics of a spring, into the interaction between these 2 nodes. And then all I have to do, as usual, is solve the system. Not to say it's easy to solve, but a computer is going to do it for us anyway. So we solve for the entire system and we get an answer. Okay, so the stiffness matrix is then, so it's assembled and it's solved. Straightforward, nice. Are we done? No. We do have one problem. So what is this value of K that we're supposed to use? If we can model the interaction of the joints as some sort of a vertical spring, then we know the mathematics of how to solve the problem. The question is physically, what is the correct value of the spring stiffness to use? What is this spring? After all, if you dig up the ground and you look at the joint, there is no spring over there. So we don't actually have a real spring. We are just approximating the physics of the interaction using a spring. And so we have to understand what is this K value, the spring stiffness value, which is going to adequately represent the physics. There are 2 approaches to understand the physics. The first is empirical and the second is mechanistic. Now I'll say the empirical one is what is used very widely. Empirical basically means it's based on experimental findings. There's no physics per se involved. It's just people collected a lot of data and they fitted it to some sort of equation, and then you keep using that equation based on data. It's not a particularly good way to do it, but it is a fairly common approach as well for joints. So we'll see both of these approaches right now. So the empirical approach, as I said, empirical basically means from experiments. And when we get to module 4 on mechanistic empirical design in about 2 lectures from now, then we'll go into much more detail on what does it mean to be an empirical design method. So the empirical approach basically means that it's from experiments. So what's happened over here is that some researchers, they went out and they collected a lot of this data. They then ran this finite element program, and so basically they had some slabs. What they did was they loaded the slab and then they measured the deflections, which is how we did load transfer. And then they went back to the lab, they ran the finite element method with different spring stiffnesses K, and then tried to see what spring stiffness value gives them the measured load transfer efficiency. So in this case, K was defined by this term ag. It's the same thing. It was just a different symbol which is applied to avoid confusion. So K was basically this ag, that is the spring stiffness along the joint. And what they did is they measured the load transfer efficiency. They ran the analysis through the finite element solver, and then they kept changing ag until the until the displacements matched the load transfer efficiency. Once they did that, they basically just fitted through a regression equation, and they got an equation of this sort, that ag is equal to K into L. L here again, I remind you, this is the radius of relative stiffness. It's one of the few formulas which I have said before that you should ideally memorize and you should know how to calculate it. So L is basically the fourth root of EH cube divided by 12 into 1 minus nu square into K. This fourth root, don't forget this one. So this is K into L, where K here is, and this is where it gets a little bit confusing, the K is not some spring constant, the K is the coefficient of subgrade reactions, the same as this K down here. So we have a multiplicity of K's going around, but don't get confused. This is the coefficient of subgrade reaction. This is the radius of relative stiffness. This is multiplied by some odd-looking empirical function of load transfer efficiency. Why do I say it's odd-looking? Well, you look at the numerator. I've got look at the exponent. I've got a 1 divided by 0.849, and then I've got a 0.012, 0.01. These are very strange numbers. There's no physics, so there's no reason why these kind of numbers should be there. If you look at our radius relative stiffness, we have fourth power, we have EH cube, we have a square. Straightforward integers. Essentially, whenever you see these odd-looking numbers in any equation, understand that this is basically a regression equation. It's come from data, it's been fit through the data to get a reasonably good fit, and then whatever number came out of it is the final equation. So that's why this is an empirical method. This is based on experiments. Whatever experiments they had, they conducted it, they did their best, and they fitted to this particular equation. What they have found, those who developed this equation, and we'll see where this equation was developed in about 2 lectures from now, but this equation, this load transfer comes from base friction, aggregate interlock, as well as Dowell bar interaction. That was their finding. So if we consider only base friction, then basically our LTE is roughly 10%. So we substitute 0.1 over here and we calculate the spring stiffness, and then we put it into the global stiffness matrix. If it's base friction plus aggregate interlock, you will always have both of them together. So base friction plus aggregate interlock gets you an LTE of roughly around 50%, and base friction plus aggregate interlock plus Dowell bar interaction. So the whole thing gets you a combined LTE, at least initially, of somewhere around 90 to 95%. You put those values in here, you get the appropriate spring stiffness, and you solve the global system as usual. The problem with this is actually from very limited data. In fact, one of the biggest shortcomings of this, that this was specifically created for cases where you had a slab, you had an aggregate base layer, and then you had a subgrade, and that to certain types of subgrade. And of course, not even to mention issues of temperature and variations in material properties, etc. So it was based on a very, very limited amount of data which was collected. Still used very widely in literature, you'll see it used in a lot of research papers, but it is an empirical function. It's actually currently being used right now far beyond what it was meant to be used for initially. Therefore, we would like ideally then to get away from this empirical approach, because we don't have a lot of data that properly explains the physics, and we are really stretching whatever data that we have. We would like a mechanistic approach which then takes away from this. So a mechanistic approach basically means it's based on physics or mechanics, which all of you have learned, solid mechanics basically. It's more or less the same thing what you learned in solid mechanics. So the mechanistic approach tries to give us some fundamental physics-based approach to understanding the behavior of the Dowell bar, or the behavior of the joint. We have actually seen a mechanistic approach in the past. We didn't go into a lot of details, but we have seen it. And that was actually the Freiberg model. So if you recall, what Freiberg did was, in order to derive his solution for Dowell bar, the interaction between Dowell bar and the concrete, he made a couple of assumptions. He assumed that the Dowell bar is an infinitely long beam which has been embedded into concrete. So we have a beam which is basically infinitely long, and it has been embedded into the concrete. So there's some amount of elastic interaction between the concrete and the Dowell bar, except for a slight section which has an overhang. So he assumed that mostly the Dowell bar is a beam, and the beam has some sort of spring interaction or a dense liquid interaction with the concrete around it. So it's embedded in the concrete, and there's a tiny amount Z which has a slight overhang between the two outside of it, and then on the other side you have the other slab. So this was the basic idea of Freiberg. We saw then that he managed to come up with certain solutions of this equation that was based on Timoshenko's solutions. He assumed this was an Euler-Bernoulli beam. He came up with some solutions which is based on Timoshenko solutions, applied certain boundary conditions, and gave us the Freiberg theory. Please go back to module 2 when we talked about dowel bars and Freiberg theory. If you don't recall this or need a refresher on this, I'm not going to repeat it, it's not too important here. But what we understand is, so Freiberg used this analytical solution developed by Timoshenko, and in particular, he assumed that this beam is an Euler-Bernoulli beam. Now, Euler-Bernoulli beams, all of you with at least a civil engineering or a mechanical engineering background, you have studied it. It's basically beams which are long and they do not admit any transverse shear. So, they are the 2D equivalent of medium thick plates, which we've studied in earlier parts of this series of lectures. So, Freiberg assumed that this beam is an Euler-Bernoulli beam. And of course, he then had an analytical solution from Timoshenko. We saw all that. But there is actually a different way to analyze an Euler-Bernoulli beam. It's actually identical to the formulation in the finite element method, but it is also learned separately within solid mechanics as something called the stiffness method. So, stiffness method and the finite element method for Euler-Bernoulli beams are essentially identical. The way we assume it is follows, that let's say this is an Euler-Bernoulli beam, and now let's say we have two nodes. So, again we are making that FEM approximation that we are dividing into nodes. We have two nodes and we can then model the degrees of freedom at each node as 2 degrees of freedom, and of course the axis here is the x-axis. Those degrees of freedom are W, the transverse displacement, as well as theta in this case, which is dW over dx. This, as you are noticing, this is a 1D or 2D analogy to what we have for medium thick plates. So, in an Euler-Bernoulli beam, then each node has these 2 degrees of freedom, W and theta. So, we have W1, theta 1, W2, theta 2, and therefore, for each Euler-Bernoulli element, we have 4 degrees of freedom. So, we have a 4 degree of freedom system. Now, recall in the finite element method, what we are basically doing is the stiffness matrix is telling us what is the connection or what is the interaction between the different degrees of freedom. So, a dowel bar is, if we model a dowel bar as a beam, again it's an assumption which we are making, it's not necessarily correct, and we will see at the end of next lecture how all of this is validated experimentally. But if we model a dowel bar as a beam, then basically our beam has 4 degrees of freedom, that was W1 theta 1 and then W2 theta 2. And then if these are attached to the slab on either side, so we have these slabs on either side, if these are attached to the corresponding nodes of the slab, then basically, and if we can put that into the global stiffness matrix, then we have successfully modeled a dowel bar as a beam. So, a dowel bar is basically a beam that connects W and theta of the corresponding slabs across a joint. That is, the W and theta of this node at the slab and the W and theta of this node at the slab are connected using the physics of an Euler-Bernoulli beam. If we can do that successfully, that is, now we define the physics as an Euler-Bernoulli beam physics. If we can do that successfully, then we have just provided one possible model. It's actually not a very good model, as we'll see, but we've provided one possible model for analyzing dowels and therefore analyzing joints. Okay, so here is an illustration of what I just said. So again, our toy problem, which is this 2 slab, each slab consists of 4 elements. Now what we have is, so previously what we are seeing is we were connecting W3 and W4 with a spring element. So we were saying there is no interaction between the theta, between the displacement elements, the interaction is between the rotation elements, the interaction is purely among the displacement elements. Now what we are seeing is that we are going to have an interaction, we are going to model the interaction between node 3 and node 4 using an Euler-Bernoulli beam. And there we make so because it's using an Euler-Bernoulli beam, what we are basically saying is that, again this is the x direction, this is the y direction. What we are saying is that W3 and W4 are still connected, and the rotational degrees of freedom along the span of the beam, those are also connected. And in this case, they happen to be theta y3 and theta y4. So our beam, which is now placed across this joint, is actually connecting W3 and W4 as well as theta y3 and theta y4. That's for nodes 3 and nodes 4. Similarly, for nodes 9 and nodes 10, we have this connection. And for nodes 15 and node 16, we have this connection. So if we can figure out what is the stiffness matrix of this connection, that is, what is the interaction between W3, W4, theta y3, theta y4 and so on, then we can just assemble it or fold it into the global stiffness matrix, And now we've added the physics of the beam to the physics of the slab. Pretty remarkable thing, but the finite element method allows us to do that without too much trouble. In fact, it's fairly simple enough that it can be programmed onto a computer. So what is that stiffness matrix? Now here again, I'm not going to go, we don't have time in this class to go into all the details for what the stiffness matrix is. If you take a class either on the finite element method which involves beam, so finite element method with respect to structural analysis, or if you take a separate course in structural engineering which is sometimes called the stiffness methods, then you will come across what the stiffness matrix is. The stiffness matrix is basically as follows. So it is naturally it's a 4x4 matrix. Why 4x4? Because we have a 4 degree of freedom system. 2 degrees of freedom here, 2 degrees of freedom here, and so the total number of degrees of freedom of the beam is going to be 4, and so our stiffness matrix is going to be 4x4. This is only for the beam. And what we've seen here is that each column and each row basically corresponds to one of those global degrees of freedom. So the first column corresponds to W3, the second column corresponds to theta Y3, the third column corresponds to W4, and the fourth column corresponds to theta Y4, similarly now enumerated for the rows. So now what we do is we simply add or assemble this stiffness matrix of the beam into the corresponding global degrees of freedom in the global stiffness matrix. Once we do that, we basically then come back to our original form, kg ug is equal to fg, and now this k includes the physics which is defined by this stiffness matrix of the beam. Once we do that, we simply solve as usual and we're done. Now, of course, I'm not showing you the mathematics of this, and it's for a simple reason that there's no point doing the complicated math. There's no point writing a 75 by 75 or 54 by 54 degree of freedom system on the slide. You're not going to follow it. We will look at more details on this and go into more specifications and see how to actually solve it using a computer program about 2 lectures from now. So just understand the basic principle or the fundamental concept of what I'm talking about, and we will get into the more mathematical solutions in about 2 lectures from now. Now, this is fine. So what we've successfully done is we started first by assuming that the joint is an interaction between the vertical degrees of freedom or the displacement degrees of freedom. We modified that, and that came from some spring stiffness. We modified that to say that the joint is actually an interaction between the rotation as well, one of the rotation as well as the displacement degrees of freedom across the joint, and the physics of that interaction we modeled using an Euler-Bernoulli beam. Okay, straightforward. Mathematically, everything we've done has been perfectly valid. The question is it correct? Is it really what would be seen in practice? That is this approach realistic? Let's talk about a little bit to understand the shortcomings of Freiberg theory. This is something we did not do in the past, but it's a good opportune moment to do it now. One thing to understand is, so Freiberg modeled his dowel, he made 2 assumptions for the dowel. He assumed that the dowel was semi-infinite in length, and that's actually why he could assume an Euler-Bernoulli beam. A beam is said to be Euler-Bernoulli basically if its length dimension is much longer than its cross-sectional dimensions. So if we have something of this sort, so if we have relatively small cross-sectional dimensions as compared to the length dimension, then the beam acts as an Euler-Bernoulli beam. This is well established, shown to be correct experimentally also, so we can perfectly make the assumption. So that was one assumption that Freiberg made, that the beam is basically infinite in length and therefore it's an Euler-Bernoulli beam. He also assumed that except for a small part which is the overhang, it is embedded inside the concrete. Is that correct? Well, let's look at this figure over here. It's going to be on the basis of our next lecture. What I have here is I have a slab over here, I have a slab over here, obviously shown in a very exaggerated way. I've got a dowel inside. One thing to understand is a dowel is definitely not infinite in length. You can hold it in your hand. It's a couple of 100 millimeters in length. It's not infinite by any means. So around 500 mm is the typical length of a dowel. So it's not infinite length. Furthermore, what we can see is that the dowel actually consists of 3 parts. There is this part which is embedded on the left side. There is a part which is embedded on the right side. And there is a little overhang section in between. Now, one could argue that okay, the parts which are embedded on the left and right, they may not be infinite in length, but they're pretty long in length. Fair enough. What about this tiny part in between? So the dowel bar, the diameter we talked about could be around 25 mm, roughly in that range. So it's in the order of a couple of millimeters. What about this length? What is the width of a joint? Width of a joint is very small. It could be 1 millimeter. It could be actually much less than 1 millimeter also. So what we have a situation is that this overhang part of it, previously we were analyzing this overhang is basically an Euler-Bernoulli beam. But as we see, this is actually a beam whose length is much less than its cross-sectional dimension. Here the radius or the diameter is around 25 mm, but the length is only around 1 mm. So this is actually not an Euler-Bernoulli beam at all. It's only an Euler-Bernoulli beam if the length is much larger than the cross-sectional dimension. And that brings us to one shortcoming of what we are doing. Everything we discussed is mathematically correct, but it doesn't actually work out in practice because we are making a mistaken assumption about the physics of the system, that is assuming that it's an infinitely long Euler-Bernoulli beam. So we would, well, then do we give up? Do we say that, okay, our physics was wrong, it's not an Euler-Bernoulli beam, let's go back to having these completely uncoupled analysis techniques using Freiburg method? No. We saw the benefits of the finite element method. We saw this extraordinary ability to actually analyze the joints as well as the slabs as one integrated system. That's not something we're going to leave behind. We just have to look for the current physics. That is, we would still like to use this model using we would still like to analyze joints and dowel bars integrated with slabs using the finite element method. But we have to ask ourselves, what is the stiffness matrix? And what that really means is we have to ask ourselves, what is the physics that is governing the behavior of the dowel across the joint? We tried easy ones, we tried a spring, we tried a simple Euler-Bernoulli beam. They have their shortcomings and they don't actually work that well in practice. So we have to ask ourselves, what is the correct physics to use? If we can get the correct physics, then we can use the finite element method to solve for it and get an accurate solution. And that's basically what we're going to look at in the next lecture. So next lecture, which is lecture 21, we're going to go a little deeper. I should warn you, lecture 21 is basically going to be the most mathematically intensive of all our lectures, but I'll try to give you an overview of it without going too deep into the mathematics. In lecture 21, we're going to learn a model which is called the component dowel bar model. It is by far the most sophisticated model which is used to analyze dowel bars in JPCP slabs. It is fairly complicated, a lot of intricacies are going to come in there, but it is what is used in practice. And after that lecture, as in lecture 23, I will show you a computer program that actually implements all of this so that you don't actually have to deal with the intricacies of the implementation. So we'll come back in the next lecture and look at a further analysis of joints using FEM in part 2. Thank you.